Cool. So welcome everyone to the first Chicago Deep Learning Workshop. So this is being streamed online too. And for people who are logged in online, welcome. Get your coffee. For the next 2 days, we're going to be working on a lot of Keras and TensorFlow and a lot of Python code to introduce you to deep learning. My name is Sri Krishnamurthy. I'm going to be talking about a couple of things, but we also have Victor Schneider here, who's going to be leading most of the sessions for the next 2 days. For people who are registering, who have gone through the paid process, we'll be sending out the slides and the code to you. For people who are watching online, watch for the updated video links on analyticscertificate.com/deeplearning. Please go to Eventbrite and register if you have not registered yet, because we have a mailing list and we are going to be sending out updates to updated streaming videos and things like that there. That way, in case you find that the particular video is not available, we're going to be chunking those videos and when we put it on YouTube so that you can actually get the updated link. So also subscribe to the channel. That way you'll get updates whenever the new video is available. So all these videos are going to be recorded. That way, in case you want to go and watch it later and kind of, work through any of the examples, you'll have it with you. So, a brief introduction to us. We are QuantUniversity. We are based out of Boston. Today is actually our 4th birthday. So we started the company 4 years ago on May 30th, and we are very excited about all those other things which are happening in the analytics space, and we've been building a lot of interesting workshops to kind of help you with adopting these interesting technologies into your day-to-day workflows. We also do a lot of consulting projects to help you kind of ramp up on various technologies to build interesting applications for you to kind of build expertise in your own companies. We've been primarily focused on quantitative methods, data science, and analytics. So I started this company 4 years ago. Prior to that, I was at MathWorks. I was doing a lot of financial engineering consulting there. Before that, I was at Citigroup, did a lot of financial analytics stuff out there. And in the last 4 years, I've taught more than 1,000 students, primarily at QuantUniversity, but also I teach at Babson College, Hult International Business School, and also at Northeastern University in the Boston area. So we have a lot of graduate students who are taking these courses. And Victor, you want to introduce yourselves for a second?
Sure. Yeah, so I've got involved with QuantUniversity for the deep learning workshops and sort of put together all the materials. Over the last, I guess, it's been like 8 or 9 months now. I studied computer science at Harvard in graduate school and taught lots of different classes there, including machine learning and pretty much all the others in computer science. I worked at edX, which is an online education nonprofit out of Boston from pretty much the very beginning. Coding, and then was product manager for analytics, and so sort of dealing with our big piles of data and trying to make sense of it. And I've done various other things before that.
Cool. Thanks, Victor. So I want to talk to you about a couple of things which are happening on the analytics side of things. So we have a couple of workshops coming up. We'll kind of briefly talk about those workshops. But one thing which is happening is the analytics certificate program in summer. So there are instructions. So in case you're interested in a full-fledged analytics certificate program, please do register in here. There are also a couple of other workshops coming up on the 8th and 9th. We have a machine learning for finance workshop coming up in New York. That one's also going to be streamed online. So please go to analyticscertificate.com. There are instructions on how to register for the machine learning for finance workshop. There's also an anomaly detection and a fraud detection workshop coming up on the 19th and 20th of June. So that's happening in Boston, but that one's also going to be streamed online. So you'll find instructions on how to register there on www.analyticscertificate.com. Okay, so that's briefly about the company and what we do. So let's get started. So Victor, you want to kind of start talking about the agenda and going from there?
Sure. All right, so I'm going to actually dive in just a minute here, but first to give a brief overview of what we're going to be doing for the next couple of days. Right, we'll start with a broad overview what neural networks are, why people are interested in them today, even though people have been playing with them for 30 plus years, 40 years now. We'll go over how to actually instantiate, sort of realize a neural network in code, specifically using the TensorFlow neural network runtime that's open source by Google, and Keras, which is a easier to use layer on top of it. And then we'll in the afternoon we'll talk about convolutional networks, which have made lots of breakthroughs, especially in computer vision, but also in other domains. And we'll talk about sequential data and how I might deal with that. We'll focus, at least for today, on text. So here's a list of some case studies. We'll look at images. We'll look at how you actually monitor a network and understand kind of what's going on, whether it's working, what kind of mistakes it's making, et cetera. Because part of the, this is a theme that's going to keep coming up. One of the challenging things with neural networks still today is that they have lots of different parameters to set. And you have to kind of know how to interpret what's going on and how to tune them to get good results. It's still definitely a bit of an art. And so these sort of monitoring techniques and tools are really important to be able to know, how you might adjust things. We'll briefly look at the effects of GPUs. That's jumping ahead, but one of the things that's made this so successful is that we have hardware now that makes it much, much, much faster to train. So we'll see how much that works. And yeah, we'll look at some more video stuff, vision stuff. Tomorrow, we'll talk about, more about neural networks, specifically autoencoders, which is a way to train if you have data that's not labeled. You can still make sense of it. We'll talk a little bit about connections to Apache Spark and high-performance computing, how you sort of might deploy this in an organization at a larger scale. We'll talk a lot more about, okay, so now that we kind of understand what's going on, how do we actually get these things to work? Learning, right? So how do you make systems that learn from experience and how that connects to neural networks? And then finally, we'll sort of wrap up with a broad summary of what's happening more on the research side these days, and yeah, what do we, what should we expect to see over the next couple of years, and where, I think where the big gaps still are as well, right? It's important that you come out of here understanding why it's exciting and how they work, but also understanding the limitations, right? It's not magic. It only looks that way sometimes. So yeah, more examples tomorrow. All right. Well, so obviously the people on the internet can't introduce themselves, but I still want to quickly go around and hear who's here in the room. Since you're here, you get to ask questions and interact, and it helps to understand people's sort of background. Dennis already said a little bit, but do you want to start and tell us where you're coming from, if there are specific things that you're interested in, either in terms of technology or maybe even more importantly in terms of the applications that you might want to apply this to?
Yes, my name is Mary, and I've been in IT for 5+ years. But I'm undergoing a career change right now, so I've been going to get so part of it is that I want to learn about machine learning. So this is one.
Okay, makes sense.
I'm Dennis Perov. I'm a data scientist at Google. So mostly, I'm very interested in deep learning. Of course, specifically, I'm looking for learning about convolutional neural networks, recurrent neural nets, and reinforcement learning. So that's kind of what my interests are right now. Like this.
And I think you mentioned earlier you're primarily, at least right now, interested in applying it to like financial data or finance problems.
Deep learning. So for the deep learning, I'm trying to apply it to financial data, like financial time series of like stock returns and things like that. So just like trying to understand like what is happening there, what may, like, can I predict something like in the future, what's going to happen?
Makes sense.
Hi, my name is Yi Jian. I'm the data scientist for IBM.
Mhm.
So that I did machine learning in the past few years. While we're doing the machine failure detection, so it's more like a classification problem.
Yep.
So we're using a traditional method. For example, I mean, the random varies, the SG boost supporting vector machine. But I would like to see if we can extend this to a deep learning network. For example, convolutional neural network or even MSTN.
Yep.
We don't know yet because we just want to try.
Right. Okay, makes sense. Yeah, sounds like we have people who've done various different levels of things. So just as a quick heads up, right, we're going to start assuming that people don't necessarily know much about machine learning. So you'll probably know some of the material in the first session, but then we're going to get into the neural network part in more detail.
So Victor, can you share a link? Can you just type in a link online so that people who are online can also put in their interests and things?
Do you want to just use Slack?
Yeah.
For that? So yes, if you're listening online, if you can put in what you're interested in Slack, then Sri can summarize maybe during the next break, and we can try to address things as they come up. All right, computers. So, right, I guess I already said this a little bit. Let me switch back to, okay. Never mind. Just takes a second to update. Trying to see if there was anything here that, yeah. So I guess I mentioned most of these things already in the previous introduction. One of the things that we're going to be going over, obviously, sort of the last couple of bullets, is actually seeing how this stuff gets realized in code. So you are not going to be an expert after 2 days, but you will hopefully have enough of an understanding of sort of how these things look in code when you run it, et cetera, to be able to learn more, right? To be able to start working, start training networks, evaluate how well they're doing, tune parameters, be really surprised at how well it works, and also really surprised at how poorly it works, depending on what you're doing. Yeah, and hopefully you're going to have a sense of how this stuff is going to evolve over the next few years. Right, so I already talked about the agenda. I'm going to continue. Yeah, we'll point to resources. Please, if you're in the room, ask questions, right? I don't want to talk continuously for 2 days. And you will learn a lot more if you sort of stop and interrupt and say, I don't understand, or, does this mean such and such? If you're online, please do use the Slack channel. We'll try to pause at the end of each session and respond if there's themes that are coming up there. All right, so neural networks. Let's start with why does anyone care, right? And basically people care, and we're all here interested in this because somehow in the last really 10 years or so, maybe less, we've gotten to the point where computers can do things that they just couldn't do before. Right, so I'm just going to go through a bunch of examples briefly. Right, we can look at images, pretty complicated images, and identify objects in them and label them. Right, including things like there's in the middle of the slide there's this car, which you can barely see. Right, it's really low contrast. The whole thing isn't even in the image, and yet it still correctly gets the bounding box and labels it. These are things that have always been easy for humans and have always been really hard for computers, but now with these techniques, you can actually do them. Right, here's a paper on classifying different types of cancer. And so I certainly can't distinguish what makes a lung nodule malignant or benign, but the computer can. Obviously trained by doctors who also can. But still, right, this is something you can do now with deep networks. You can do there's a lot of excitement about things like self-driving cars. You can actually label each pixel in an image with a particular category, right? See what's road, what's pedestrian, what's car, what's background, et cetera, which is obviously necessary if we're going to make these things work. And beyond vision, the world's best sort of deep neural network-based speech recognition systems now are actually better than humans in a number of benchmarks, in a number of languages. Right, so you can take this sequential data, audio, and train it to recognize speech. Yeah, and so this was a few years ago. I guess I should get an updated one. Actually, I was looking at this again yesterday. Baidu's speech recognition thing is better than humans for Chinese, which is a really hard language, at least for people who don't speak Chinese, maybe, to understand. And similarly for English. This is more on the research side, but you can actually start to now get captioning systems. So it not just gives you labels for the objects in the image, but actually tries to tell you a story of kind of what's happening. And we'll come back to this again tomorrow. I think it's interesting to look at both the successes, right? On the left here, you can see things that got really, really well. Like, look, people playing a game of Frisbee, elephants walking across a field. It's magic, right? It's figured this out. And then you look on the right at some of the mistakes. And the one in the middle, like that's a refrigerator filled with lots of food and drink. Because no human would make that mistake. You can kind of maybe see where the computer got it. Right, there's white and there's lines and there's random colored stuff in the middle, but clearly it's not doing vision the same way we're doing vision. But still, research area, making progress. This is also still kind of a research area, I think, in many ways. But for text applications, you can read. You can make a network that can read this kind of short story and then answer questions about it. And I actually don't exactly remember what those numbers are, but basically it sort of tracks the various objects and the relationships between them, and can then figure out like, oh, okay, the football, the last time it was mentioned was in the second line, but the football was mentioned, but then the person that took it moved around after that, and so I can make those connections and actually give you a correct answer with some good probability. So people are trying to use these techniques for, question answers, not for obviously toy stories like this, but for example, for data mining or knowledge databases, right? If I have a, I don't know, IBM Bluemix support site with a gazillion documents in it, and you want to find the right one, and ideally even find an answer to a question that maybe isn't described in any one of them. How do you synthesize that? I couldn't find great visual, so I went for recursion instead, right? But Google has been, talking for a couple of years now about how this stuff is starting to really permeate their business, and not just Google, but I picked them as an example. In particular, a lot of the stuff they're doing with search ranking, obviously is still based on their old methods, but they're augmenting it with neural networks to figure out, okay, how do I give you really the best results? Both for things like visual search, where the stuff we just saw comes in really useful, but I think also for ranking. So probably neural networks were involved in answering this search query for deep learning for search ranking. Other applications where I couldn't get good visuals, but lots of people trying to do AI, machine learning, deep learning, in particular for security. That can be hard because outside of the big companies, you don't really have data for this. But if you are in a company where you have lots of network logs and things like that, you can try to apply these techniques. And then, moving into things that are more interactive. There's been a lot of work on robotics and reinforcement learning. I guess we started a little late, so I'm not going to show this video today. But well, we're gonna talk about this tomorrow, so we'll see it in more detail. But rather than trying to program these robots by hand and say, okay, here's exactly how you grab things, we now have these systems that use vision to actually make sense of the scene, and user reinforcement learning algorithms to learn how to, for example, grab objects and move them from place to place. And you can actually see it's kind of fun. This is on the side. I just had a daughter like 4 months ago, and it's kind of amazing how similar her like learning to grab things is to these robots. Like they flail around, and then slowly they kind of get roughly to the right place, and then next thing you know, they're actually grabbing things. This is also should be updated as of a few days ago, a few weeks ago, I guess. You know, multiplayer kind of situations, right, where it's not just robot and environment. Now it's adversarial games, poker, Go, etc. These techniques have been applied to, well, at this point, really be better than humans, right? So AlphaGo last week, I think, won a match against the world champion, who, you know, is maybe slightly better than Lee Sedol. And he was like, yeah, basically, there's really no point playing against computers anymore. Now, you know, I'm going to focus on playing against humans and running from the computers because they're just better. So obviously, maybe we don't really care that much about playing games, but the underlying ideas for how to, you know, make the system work will hopefully be applicable more broadly. All right, and then finally, the other reason that people are interested in this, I think, outside of, you know, Google, for example, is that you can write a neural network and fit it on data and predict stuff in this code that fits on one slide, right? So now there's tools and infrastructure easier to, not to mention pre-built products, but even if you want to write stuff yourself, you don't have to start from scratch and sort of write thousands of lines of code to get anything. There's lots of debugged, high-performance libraries out there, and so you can stay at a higher level and sort of think about for your problem, not, you know, how to take derivatives and so on. So well, hopefully by the end of today, you will understand this code, but we're not going to go through it right now. Okay, I do want to make sure that even though we're focused on deep learning here, we have a sort of a little bigger picture. All right, you'd mentioned a bunch of other machine learning things that you've been trying in your application, so we'll see some of them, right? Really big picture. This is a quote I really like from Peter Norwig, who's the director of research at Google now, and, you know, literally wrote the textbook on AI. Computer science is doing the right thing efficiently when we know what to do, right? So there you're concerned with, okay, how do we sort of code algorithms and yeah, do what we know what we want. AI is doing the right thing efficiently when we actually don't know what to do. And so then somehow we have to get the computer to figure it out. And I cribbed from Wikipedia, right? There's a whole ton of different things that fall into AI. Right, sort of deduction and reasoning, how do you represent knowledge, how do you plan, how do you learn, et cetera, et cetera. Lots of different problems, lots of different approaches. You know, you can see deep learning if there is one of those bullets. A number of the others are actually also related. But yeah, you know, you were saying you want to try to use deep learning for your problem, and that may be a perfectly reasonable thing to try. But also, it is important to remember, you know, just because you have this big hammer doesn't mean you should use it everywhere, right? There are plenty of situations where one of the other approaches might actually be more reasonable. And sort of be an expert in AI, you do need to understand more of them and be able to decide which one makes sense. Okay, so what is deep learning all about at a very, very high level? And it's sort of about this, right? Can anyone tell me the answer to this multiplication question? Kind of annoying, right? Is it easier if I write it that way? Right? So how about, can anyone tell me what this image is showing?
Something like on the outer edges.
You can kind of get a sense just because, you know, some of the digits are bigger than others, right? You can tell 2 digits, 3 digits. I mean, I made it small so I could fit the numbers on the screen, but is that easier? it's too pixelated, but right, you can kind of see there's a panda there. And our visual system does much better with that picture than it does with a whole bunch of numbers. And so ultimately, the point I'm trying to make is that if you can represent a task in a way that makes it easier to do, it makes it easier to do, right? And so for us, for a visual system, right, I'd much rather see a picture of a panda than a whole bunch of pixel. And I'd much rather do, computations using Arabic numerals rather than Roman numerals. For computer, we want to do the same thing. And so essentially, the really big idea for neural networks is that we're going to have the computer figure out how do I make a representation of whatever problem you're trying to solve that's easy to deal with. And then, then it's going to be easy to solve. In some ways, support vector machines and many other things in machine learning are similar, right? Where support vector machines say, look, I'm going to make linear separators, but in this weird high-dimensional space. And so if you pick the right high-dimensional space where you can easily linearly separate your beta classes, then your problem becomes easy. And the trick is going to be that, it's hard to describe, what is a good representation, right? If I ask, okay, what does a cat look like? If I get a description of an image that says, look, there's an animal and it has, 4 legs and a tail and it looks really, really cute and, has pointy ears and whiskers. In that space, it's probably pretty easy to determine, cat from elephant from whatever. If I give you 1 million pixel values, it's much harder. And so the question is, how do we get a computer to learn to take those 1 million pixel values and translate it into something that's more like that sort of feature vector, essentially. And then you can pretty easily do the classification. Same thing for, what is a valid English sentence? People in linguistics have been arguing about this for a long time. And whatever they say, if you look at Twitter, and things that people understand just fine, they're not describable by traditional grammars. And for things like robotics as well, right? It's very easy, right? Just figure out how you walk, encode that into your robot, and we have a robot that walks. But it's really hard to actually describe how I'm moving my muscles so I don't fall over while I'm standing there. And again, we're going to try to have the computer just figure it out. And again, this was just for intuition. We'll come back to this picture a little bit later. But basically, we're going to have these networks, and they're going to start with raw data. So this is an example from face representation. You take the pixels of an image like this on the left, where I don't know exactly how many, but you have a few hundred pixel values. And the lower levels of the network are going to extract out sort of low-level, easy-to-compute features like, okay, there's a line over here at this angle. There's this particular texture. There seems to be a particularly dark region at this spot or at that spot. And then given that, it becomes easier to then compute slightly higher-level features and say, okay, you know what, over here, there's something that looks kind of like an eye. Because there was a dark area surrounded by a light area surrounded by another line right above it that's sort of curved down. It's like an eyebrow. You can see that, right? Or something that looks like a nose, something that looks like sunglasses, et cetera. And then once you have those features, now it becomes easier to actually say, okay, you know what, this is a face, right? And this is a face with a mustache, and this is a face with, that's shifted up or down, et cetera. And so we're going to have this hierarchical representations that are going to get more and more complicated as you go down into the network. And in the end, once it's figured out this high-level representation, now if you want to do some kind of face-related task, for example, identifying that these two photos are the same person, it's much easier if I can look at that last layer and say, okay, you know what, these features are pretty much the same. Whereas if I give you the pixels, every single one of them is probably going to be different. So that's the basic promise, is that neural networks can learn these kind of representations and do it automatically, right? So you don't have to sit down and what people did for many, many years in vision was try to write down, what does an eye look like? What does a nose look like? And then, oh, well, what happens if you're looking at it from a side or in the dark or with a strobe light on? And if you have enough data, this can figure it out. Brief history. As I mentioned earlier, right, these things are not new. people started thinking about how do we kind of model, really, really simple models of what neurons might be doing in our brain, and using that for learning back in the 40s, 50s, and 60s. People started doing multi-layer, like really things that look kind of similar to what we're going to be talking about for these 2 days back in the 70s. And got some, had way too much hype. And so then couldn't live up to that hype. And so then people stopped funding it, and people decided to start doing lots of other things. But did make some progress. In the early 90s, there was some progress on like simple vision tasks. So for digit recognition, for example, I think the Postal Service was already using this to read envelope addresses and so on back in the 90s. But again, people sort of made too much hype about it, and got excited about other approaches like boosting, support vector machines, et cetera. And when I taught neural network, I took machine learning class, what was it, 8 or 9 years ago now? We taught neural networks, but we kind of said, no one really uses them. They're kind of hard to tune. Typically, people get as good or better performance with these other methods. So you should probably know about them. Today, I would not say it that way, because there were a few algorithmic improvements, and really hardware and data are the other two big pieces. We're now, I think it depends on the field. In about 2009, people got sort of state-of-the-art results in linguistics and text processing. And about 2012 was the first time there was a really big jump over state-of-the-art in vision using neural networks. And since then, that's sort of even expanded further. There are some folks who sort of basically wouldn't stop working on this stuff from the 80s and kept doing it, and now they're famous and working at all the big companies. Here's 3, right? Jeff Hinton, Joshua Bengio, and Jan LeCun. A couple of them are up in Canada, which is also kind of interesting. So what changed, right? Jeff Hinton summarized this, I think, pretty well. We had way not enough data to train these networks. Even if we had more data, we didn't have computers that could do it in any reasonable amount of time, right? So computers are 1 million times faster than they were in the 80s when you consider the parallelization. And then there were a couple of algorithmic things that we'll talk about a little bit more for how you initialize a network, and for how you, nonlinearity, we'll understand that hopefully pretty soon. And I guess, the other piece I briefly mentioned earlier is that on the right here, we have all these different, and this is by no means a comprehensive list, frameworks out there that you can use to build neural networks. And so part of the reason why they're growing so fast is that people are excited about the potential, but part of it is that you can just go and start coding, and don't have to sort of start from scratch. Sri always likes to talk about this NVIDIA DGX-1 toy. If you have $100,000 lying around, I strongly recommend. No, I don't actually recommend. But now they're making custom hardware that's sort of basically a deep learning supercomputer in a box with some ridiculous number of GPU cores, all prepackaged. And so, if you're doing real kind of industrial scale deep learning, IBM actually I think has I forget what it's called, a Minsky or something box that's pretty similar.
There was a trading show a couple of weeks back in Chicago, and NVIDIA was there, and they were mentioning that there's actually a smaller version of it for prototyping being made available. You can actually prototype it in a smaller version of the DGX-1, and then you can kind of scale it up on DGX, the real DGX-1. So apparently they're trying to package more GPUs that can run more experiments on-prem, that have them doing everything.
Yeah. For people on the stream, Sri was just saying that apparently NVIDIA is saying that they're going to already have a smaller version of DGX-1 that you can prototype on before you want to spend $100,000. Yeah. All right. So how does this work? Right. We're going to start with the cartoon version. And before we get into it, I want to just do this high level level setting. So obviously you're going to know about this, but I don't know how much you've done machine learning, and I don't know how much you've done. Right, roughly at a very, very broad high level view, in machine learning, where you're trying to give a computer a bunch of data and have it figure out something, you can break it up into kind of a couple of buckets. One is unsupervised, where you just give the computer data, and it's not labeled, and you ask the computer to basically organize the data in a way that makes it easier to ask questions about it. So for example, you can say, can you cluster these data points and tell me which ones are similar to other ones? Or can you set it up so that if I give you a new data point, I can ask you, is this like some of the others or not? Or is it sort of an outlier? So that's unsupervised. And then another big category is supervised. Here, I have data that's labeled in some way. Right, so I say, look, here's a bunch of photos. These are faces. These are not faces. And now I want you to learn to distinguish faces from not faces. So given a new image, give me that label. Right, so that's a classification problem. Sometimes you have regression problems where you say, here's a bunch of time series stock data. I can tell you what I'm interested in volatility, so I can tell you what volatility was at various different times in the past. And I want you to learn to predict, okay, given here's a history, what's going to be the volatility tomorrow, right? So here you're making sort of X, Y pairs, and you're trying to predict Y from X. Broad things to keep in mind as we go through. So the cartoon version of a neural network we're going to start with is going to be for supervised learning. And we'll talk more about unsupervised tomorrow. For the most part, most of the progress, I don't know if that's fair, but a lot of the progress and a lot of the big results have been in supervised learning. It's easier in some ways. So imagine we're going to start with a bunch of photos, right? Kitten photos and puppy photos. I could have used anything else, but these are cute, so why not? And we're going to try to go to predictor, give it a new photo. This is important, right? That word new. You can't just predict the stuff you already saw. That's cheating. How do I know whether that's a puppy or a kitten? And again, this is a task that for a human is trivial. And if you went to a computer vision expert 10 years ago and said, how well can you do? Like, well, we could probably get 65% on this two-class thing, right? But it's really, really hard with generic photos in unconstrained environments. Yeah, and so we're going to have this network. We're going to put our pixels on the left. So, right, this is a 3,000 by 2,000 image, so it's like 6 million pixels. So you have 6 million inputs. Well, actually, for each one you have a color, so three numbers. And we're going to compute in the middle things that hopefully will be like, oh, is this an animal at all? Does it have fur? Does it have pointy ears? Is it really cute? Etc. And then combine those features to decide whether or not it's a kitten. And so if it's a kitten, then that top right circle should have a high value. And otherwise, maybe it's a puppy, has a high value. There was an XKCD comic a few days ago that I really liked about this, right? So machine learning systems, many of them, but certainly deep learning in particular, is really kind of like this comic, right? You take a bunch of data, you have a giant pile of linear algebra with some parameters in it. You stir the data in that pile and those parameters until it looks right, and that's your system. So really what we're going to spend the next couple of days talking about is, how do you actually make a pile of linear algebra? Technically, it's a pile of slightly nonlinear algebra. And how do you adjust it so that you actually get good results? But if someone asks you what you learned about, just point them to this. And yeah. All right, so how does this actually work? Let's start with linear models. Here's the world's simplest neural almost network. Right, you take your inputs. So we're going to have x and y vectors again, right? So our x vector has some length, in this case 2. And we're going to just take each of our inputs. We're going to multiply it by a weight. Note this one at the bottom here. That's a way to make it, not necessarily have to go through the origin, just a bias to be able to shift the whole thing up and down. And we do a weighted sum. And learning really is, like, what does it mean to learn? It just means to figure out what good weights are, so that when you do this weighted sum, you get an output that's close to what you want. And so if I have a whole bunch of different x and y pairs, for linear regression, the question is, OK, how do I set my weights so that on average I get a pretty close approximation to the y I want, given my input x?
So there was a question here earlier.
So
we were talking about image recognition. Participant wants to know what happens to CAPTCHA. Is it deep learning involved?
So question from Slack is, what happens to CAPTCHA? Yeah, CAPTCHA is kind of screwed. Essentially, I mean, you may have noticed over the years, CAPTCHAs keep getting harder because computer vision is getting better and better and better. And so, yeah, actually, these days, I think people are not using the type-in CAPTCHAs as much. They're using other visual tasks that are harder. I remember recently seeing some that are like, identify whether or not this photo has a storefront in it. Partly because Google wants to get more labeled data, but partly because that's still a task that's actually quite hard to build a good classifier on. Because it has sort of a high semantic component, right? It's not just is there a building? You have to actually understand what kind of building is it, an office or a store, et cetera. But yeah, CAPTCHAs are doomed. OK, coming back to this. Right, so if you want to do a classifier, you might say, OK, I want to give me a positive output if I want the answer to be yes, and negative if I want the answer to be no. And then, yeah, I talked about the bias weight. Right, so this gives us a linear classifier, where if my data is linearly separable, if you learn good weights, you can basically make it so it gives you the right label for a new point. Sometimes your data is not linearly separable, or not perfectly linearly separable. Right, this is still a pretty easy case where you can say, you know what, I'm going to figure out some way to penalize it for mistakes and ask to find the best line. Yeah, so there's this notion of a loss function that says, what is it that I'm actually trying to optimize here? Right? Do I want to minimize the number of mistakes I make? Or is a mistake that's really, really far away actually worse? And so I want to minimize some kind of distance function. If it is a distance function, do I want to minimize square distance? So I penalize things that are far away a lot, or just linear distance. SVMs, for example, say, look, I want to minimize or maximize the margin. So I want to make a line that's as far away from the two sets as possible. It just sort of intuitively captures the idea that if points are separable, I want the line kind of in between them, not touching one or the other set. So we'll talk about loss functions more as we go through. Well, first let me pause there, actually. Any questions? Does that make sense before we move on to more complicated things? OK, so multi-class.
Use some tests. Let people check some questions.
I will. We actually have some coming up in just a minute. So many problems.
Online too, so for people who ask questions on the Slack channel, in case there are questions, you can just make an announcement. I can track those questions and get back to you.
Sure. I mean, you can also just type it into Slack. People in Slack or anything out, if you want to ask questions, put them in Slack. Right. So a lot of what we're going to be talking about for classification is not just going to be binary, but it's going to be multi-class. So here's a question, actually. How do we deal with this, right? So we just talked about, we have the simple linear model, and if the output's positive, then we say, yes. Otherwise, we say no, 1 or 0. But what do we do if we have 10 classes? So here's a data set that we're going to see a little bit. Basically, the task is to take these visual images of letters from A to J, I think, whatever the first 10 letters are, and tell you whether or not this is an A, B, C, D, et cetera. So how might we represent that mathematically?
Represent what, the loss function?
No, how do we change our network that we saw before? Where was it? Right. So here we had a binary classifier. We just got an output that said yes or no. Now I want an output that says A, B, C, D, E, etc. Right. So instead of 1 Y, we're going to have 10. You could actually just do 9. Very slow. Here we go. Thought I'm missing a picture. No, I guess I'm not missing a picture. Fine. Right. So we're going to have, instead of just one circle and one set of weights for a classifier, we're going to have one for each class, and we're going to learn different weights for each one. Right. So here the inputs are 28 by 28 images, so 784 pixel values. In this case, it's just black and white. So you have 784 numbers. We're going to have 10 outputs, right? One for, is this an A, is this a B, is this a C, etc. And we're going to do the same thing, right? We're still going to take a bunch of weights for each class and a bias. And so for each one, we're going to have this weight vector, W1 to W10, which altogether gives you a weight matrix. Multiply it by your input vector, add a bias, and that's going to give us a number for each Y. Question?
Yeah. So here you mentioned that in this case, say we have 10 classes, so we have 9 outputs, right? Because that's,
yeah.
10 is obsolete. But if you sort of like misspecify and put 10 classes, so like you have an additional, an additional class. The neural network will not blow up, right? But like that's like an additional thing. So like if you're going to be predicting stuff on the new sets, you're going to predict all 10 of them, so they won't probably add up to 1. Right? Or something. It's like
so good question. Hold that thought for a second. So the question is, right? I think summarizing, if I'm trying to predict the probability distribution over 10 numbers, I can actually specify just 9 of them, and then the rest is 1 minus the sum of those. But here, the way I've drawn it, I'm actually going to have 10 numbers. And how do we guarantee that they add up to 1, and so on? So for one thing, right? Is there any guarantee at all that this adds up to 1 so far? Right? No, not at all. Right? You could actually have, well, I mean, these could be arbitrary numbers. In particular, many of them can be high, many of them can be low, they could be negative, etc. So we need to do something to convert this set of numbers into an actual probability distribution, and that's typically what people do. So I think that's actually maybe the next slide. Yeah, we're going to use this softmax function, which, given a vector of numbers, arbitrary numbers, positive, negative, big, small, etc., gives you a probability distribution. And you don't have to worry about the math, but basically it's just take e to the gj for each element, and then just normalize. And so the intuition is it squashes an arbitrary vector into a positive vector that adds up to 1, so into a probability distribution. And the key things it does is it preserves order, right? So basically, big numbers are going to have high probability, low numbers are going to have low probability. And there's sort of theoretical reasons why this is a particularly good function to use. But
sometimes they use negative number.
e to the anything is positive, right? Because e, think about
they sort of use e to the minus zj instead of positive zj.
So
the exponential function. Anyway.
There are various ways to do this, I guess. If for some reason you wanted to treat small numbers as to have high probabilities, right, you can flip the signs. So there are things you can do Sometimes you might want to add some constant to sort of give everyone a benefit, et cetera. In this case, the idea is the network should figure out weights such that the input, the y values we feed into this thing are reasonable. But yeah, so we're going to take the softmax here. Sorry. Right. So we take our input vector x, we multiply it by the weights, we get the y's. We feed it through the softmax s of y, and now we actually get probabilities. So that, I think, hopefully addresses your question, right? And now we have, this makes it easier to represent. So you just get your 10 numbers. If you want to look up the probability of any of them, you just look it up. You don't have to do any additional arithmetic at the cost of representing one more explicitly.
So there was a query earlier on this. If you go back a couple of slides,
Yeah.
the similar slide which had like the y1 weights.
Yeah.
There was a b1 which is the bias. So should that be b1 or bj? Was the question.
Oh, sorry. Yes, that's a typo. That should be bj. Good job, internet. Finding our mistakes. Okay, so now we have probabilities. And one thing that this does is, well, let's come back to this, right? So what we want to do is we want to say, I'm going to learn weights that make you get good output vectors, right? Good probabilities. And what does that mean? Right? For this particular thing, it's an A, right? There's no question about it. It's definitely not a B or a C or a D or et cetera. And so what I want is I want the probability of A to be high, and I want the other probabilities to be low. And what we're going to do is what's called a one-hot encoding of labels. So we're going to take, when we know that this particular image is an A, we're going to represent that as this vector that has a 1 in the first entry and 0 everywhere else, B, a 1 in the second entry, C, 1 in the third entry, et cetera. And so now I can actually put that label next to my probability vector. They now have the same size, and compare how close am I. So now we need some distance function, right? This is back to that loss functions discussion earlier that says how close is this particular probability vector that we got with the current weights for this A to 1 and a bunch of zeros afterwards. And so there's a standard measure that people use for these kind of classification functions called cross-entropy. I don't remember if I even put the expression in here. You can go look up the formula if you want, but the nice thing about using these packages is you just say, I'm doing classification, use the standard stuff, and it'll implement it for you. It's basically looking at the measure of like how much information, how much entropy there is between the two distributions. And it's small if your probabilities are very close to your label, and it's not small if they're far apart. So, now we have, this is a multi-class logistic classifier, something that people have been using for decades. It's a linear model, right? You have weights and biases to earn. You get probabilities. You compare them to your labels. Well, I guess to my previous point on not doing things that are too complicated, try something like this first in many problems, right? Before you start doing complicated neural network stuff. If a linear model solves your problem, then do that. So exercise, right? I'm going to go back to the previous slide, and I want to think about what are the dimensions of each of these vectors or matrices, so that this is one of the things that's useful to keep in mind as you're writing your own systems. Kind of how much data is flowing through your network at various points. There's always going to be, okay, what's my sort of current representation of my input, and therefore, how many weights am I going to have? And this is a helpful way to debug your networks. So let's come back to this picture. Easy question. How many dimensions does X have? 784, right? I mean, x1, x2, x3, x4, x5, 2x, 784. In general, it's how big is my input, right? However I represent it, whether it's pixels or audio samples or financial data or whatever it is, I'm going to feed my network some amount of data at a time. For now, it's fixed. We'll later talk about what happens if it's not always the same length. So then I'm going to have these weights. How many weights do I need to multiply all of my inputs to get WX there? And then we're going to add biases. 10 times 784, right? For each of my outputs, for y1, I'm going to need one weight for each of my inputs. So that's 784 weights for y1 plus another 784 for y2. So 10 times 784. How many biases? So the B, right? So for each of my circles, basically, so for each of y1 through y10, I have a bias. So that gives me a way to say, you know what? For example, you can think of it as a way to say, A's are just more likely. In my data set, like there's A's all the time, and so if I'm not sure, I should make it an A. And so then the network might set the bias for A to be higher than the others. So right, the number of biases is equal to my number of output nodes, and the weight is the product of the size of the input times the size of the output. How big is the probability distribution? How long is the S of y there? 10, right? For each of my outputs, I have a probability. And then the labels, when they're one-hot encoded, also the same length, right? Got all of those right. Huzzah. So now the question is, so far I've been hand-waving about learning, right? And picking good weights. How do we actually do that? And so what we're trying to do is we're trying to find weights and biases that minimize the error given my X and Y pairs that I have in my training data, and given the particular weights and biases we've selected. Also with this caveat at the bottom here that minimizing the training error is actually not quite what we want, because what I want to do is I want to predict new things, not get the right answer on the X and Y's I already have, but we'll come back to that. Basic idea for how people train neural networks is gradient descent. And again, I'm not going to get into the calculus in detail, but you pick some random W and B, and if you remember that Jeff Hinton summary, how you pick it is kind of important. You figure out the derivative of this error function with respect to each of the weights, and then you take a step in the opposite direction because you want to reduce your error, not increase it. Right, and so you think of it as saying, okay, if I wiggle this weight a little bit up, make it bigger or smaller, what happens to the error? And then wiggle it in a direction that makes the error go down, and then just repeat. And so the intuition that's, I think, useful to have, especially if you haven't done lots of sort of numerical optimization before, is you're wandering around in this multidimensional space, and you're trying to find low points. Right, so even for this toy example, we had something like 7,500 parameters, and you have to wiggle each of them. This is just a two-dimensional parameter, right? So there's like this position, and then the height is the value. And so you're saying, okay, if I start over here and I take small steps in the direction that goes downhill, how is it going to work, right? Am I gonna find a good value? So good means low error, or if in the visual analogy, it means a point that's sort of as low as possible. So what are some of the challenges you might get into if you're trying to find the lowest point in the space, and your algorithm is pick a random place and just walk downhill? Local minima. What does that mean? Right. You're walking downhill. Imagine we're in this room, and I apply this method. I'm like, okay, I'm walking downhill. Well, there's no downhill. Everywhere seems completely flat. So I found a place that seems as good as possible. And yet, if I walk out of this room and around the corner, there's some stairs that can take me, I don't know, 100 feet further down. And the same thing can happen here. You start walking somewhere, you find some little hole in the ground, and there's no more downhill from that spot, even though you're still much, much higher than you actually could be. So worrying about local minima is, is useful. Some of the mechanisms that we'll talk about, help solve this problem. You're basically never going to be guaranteed that you found the optimal point if you're trying to optimize thousands or millions or billions of parameters. It turns out, for very strange reasons that we're only starting to understand in the research world, it actually works. It wasn't obvious that it would work, but it kind of does. You use gradient descent with a few tricks on these billion parameter networks, and you get stuff that actually does something reasonable. It's kind of magical. OK, so that basically gives us our loop, right? We set up our network, we measure our training error, we wiggle the weights a little bit in the right direction, and then we repeat. And when the error doesn't go down anymore, we stop. And if we're happy, then we're done. And if we're not happy, then we have to go change something and try again. So enough of me talking for now. Let's take a quick break and look at, have you actually go play with this. So I'm going to change the screen sharing stuff.
So you're going to take a 10-minute break now?
Well, I'm going to do this exercise.
OK.
So people on the internet, I strongly recommend doing this as well. Go to playground.tensorflow.org. I will, yeah. Let me stop this. Let me go back to screen share. OK. Playground.tensorflow.com or .org? I can't remember. .org. Yeah, OK. However, Google saved me. OK, I'm going to see if I can drag this to my. No, fine. So can you see that in the stream?
Yes.
OK. So is everyone there? This is a neural network playground that we'll use a few times during this workshop. And we'll see sort of by the end of tomorrow, you should understand all the things. For now, hit minus here where it says hidden layers until it's 0. And that gives us the picture we just talked about. So basically what it's doing is it's saying, I have some data generated from some distribution. So in this case, this is the simplest one, right? There's some points toward the middle that are labeled blue, and some points toward the outside that are labeled orange. And I feed in my network. In this case, it's just a linear network with the x value, right? So how far along am I to the right, to the left, and the y value, x1 and x2, up and down. And on each of these edges, there's a weight. So it says take this value of x1, multiply it by this weight, and add it to this other weight multiplied by x2. And that gives us an output represented by the color here. And so you can actually, you can run training, but you can also just change things by hand. So I can say, OK, let me change this weight to be 1. Let me change this weight to be -1. And so now I have a classifier that's has low values up in the top left and high values in the bottom right. So you could try by hand. Obviously, you're going to have a hard time with this data set. If you want, you can switch to this data set, for example, to set the weights. You can also hit this play button, and it's going to run gradient descent for you and figure out, in this case, it's a linear model, so it's very easy. It says, OK, look, if I set the weights like this, so 0.8 and 0.6, then I get this line that separates out the two data sets. Well,
What is the play button? Generate the iteration.
sorry, where's which button?
The play button, then you can.
Oh, play up here. So you can do one step at a time, or you can just hit play and it'll go train. Again, for this model, right, where there's no hidden layers and the data is linearly separable, it stops very quickly. You can try, and again, we'll understand this better later, but so you can try, for example, the circle model. That's probably not going to work very well, right? With a linear separator, just x and y, x1, x2 inputs. It can try to find some line, but there's no line that's going to separate these two very well. I think maybe let's stop here. We'll come back to it in a little bit. Let me sort of understand, other things we can do. But we'll play with this more today, and I think also a little bit more tomorrow. General point, if you're ever sort of thinking back to this in a few weeks or months, like, oh, I'm trying to remember, how does this thing work? Like, what's the effect of number of layers or number of nodes? This is a really great tool to play with it kind of in a small setting. You can train the network instantly, and you can really get an intuitive sense of what happens. OK, so I'm going to go back to the PowerPoint. Can you check? So I'm now supposedly sharing my entire screen. Is it showing this, or is it showing the presenter view?
Still showing it's not, okay, now you see this.
OK, perfect. Then I don't have to keep fiddling. All right, so we promised you deep neural networks. That's why you're here. And so far, we did linear regression.
Can we take a break now? Like maybe 10, 15 minutes? It's,
sure.
It's 9:10, or rather 10:10.
Yep.
So we can take a break till 10:30.
OK,
Yeah. So
that's fine. All right, so we'll come back to neural networks. I'm going to stop the video then.